The Michelson-Morley experiment is probably the definitive experiment of the 20th century, certainly a very, very famous experiment, as Michelson and Morley tried to measure the speed of the Earth through the ether being the medium through which light travels, and as the Earth rotates around the Sun, it must at some stage in that rotation be travelling against or some movement between it and the ether wind. And so what they attempted to do was they attempted to set up an experiment to measure the speed of the Earth through the ether wind, and it was a very, very clever experiment because the speed of light is very fast and the speed of the Earth as it rotates around the Sun is fast, but relatively compared to light is quite slow. So they needed a very sensitive piece of apparatus to measure our speed, and that piece of apparatus is very ingenious. It basically races two light rays against each other. They go through this central device, which is a half silvered mirror, so half the light ray gets reflected and the other half passes straight through. They then get reflected off these solid mirrors here and come back and recombine back here in the half-silvered mirror, sometimes called a beam splitter. Then the light beam then arrives at this point here, which is the detector, and as it arrives at the detector, those two light beams can interfere with each other because those two rays of light are waves and create an interference pattern. Now, if one of those light rays is travelling with the ether wind and the other one's going across the ether wind, they're going to arrive at a different time. Now, to understand why they arrive at a different time, we're going to have a look at an analogy using boats. Now, the Michelson and Morley experiment was designed around racing two light rays, one with the ether wind, one across the ether wind, and trying to work out what the speed of the ether wind is by the difference in time as they arrive back at the original location. So we're going to use an analogy of two boats here. We've got our green boat here, we've got our red boat here, and we're going to send them on a boat race. We're going to imagine that up here we've got the speed of the river, the stream running downwards. That's our ether wind, if you like. This boat here is going to race against the ether wind on the way up and then turn around, and of course it's got a bit of a tailwind here, a current helping it to get back to the beginning place faster. This one here is going to try and race across, turn around and come back. But of course this one here, if it's going to make it straight across, is actually going to have to drive at some kind of angle to make it across, because otherwise it would just be swept downstream. So in order to maintain a straight line across, it's going to have to come across at an angle like that and come back at an angle like that, and both of them are going to get to their starting place, and we're going to see which one arrives there first. Okay, so there's our two boats heading off on their journey. Let's think about the green boat first. Okay, so the green boat is going to head off up the river with some kind of velocity. Let's say that both boats can travel at 5 meters per second. Well, if we look at the vector sum of this boat's velocity on the way up, it's going to have a net velocity of only 2 meters per second because the rivers are going against it at 3 meters per second. It's only capable of 5 meters per second, so it's got a net speed of 2 meters per second. And if we think about speed or velocity as distance divided by time, then we can say the time one for the journey up is going to be the distance, 2,000 meters, divided by the speed, which is 2, which is going to give us 1,000 seconds for the journey upwards. The journey backwards, let's call that T2. Well, let's think about the journey backwards. Well, on the journey backwards, remember, our boat is going to be travelling backwards, which means that those two velocities are going to add. And so now we've got 5 plus 3, which is 8. So on the journey on the way back, it's going to be our 2,000 meters divided by 8 meters per second here, which is going to give us 250 seconds on the way back. And so our total time for the journey is going to be 1,250 seconds for the green boat. Okay, so the green boat's velocity, its total time, I should say, is going to be 1,250 seconds. Okay, so let's think about this not from the green boat's perspective, but now from the red boat's perspective. Now the red boat is a little bit different. It's going to have to head across the river, as we said, heading upstream a little bit. So it's going to have the same capacity as the other boat. It's going to travel at 5 meters per second, but it's got a down the river component. Well, it's got to have an up the river component to overcome the down the river component of the current. So it's got to be able to move up the river at 3 meters per second. And if we look at this, if this is 5 and that's 3, we can set to a right angle triangle. That's going to have a speed of 4 meters per second on the way over, and by symmetry, a speed of 4 meters per second on the way back. So if we think about its formulas here, so it's time 1 for the journey over. It's going to be the distance, 2,000 meters divided by 4. So that's going to give it 500 seconds for T1, and T2 is also going to equal 500 seconds. And so for this boat here, its total time is going to equal 1,000 seconds. And so from that, we can pretty clearly see that the boat going across the stream is always going to beat the boat going up and back with the stream. And the faster the current, the greater the time difference between those two, and the greater the difference of arrival time back at the starting line they would be. And from that difference, we'd be able to measure what the speed of the river is. Well, this is the idea that Michelson and Morley were applying in their experiment as they tried to measure the speed of the Earth through the ether. Okay, so let's try and put together everything about the Michelson-Morley experiment. Very, very clever design. They were racing two light rays against each other, one at 90 degrees to the other, rotating that whole apparatus. So at some stage, one of the light rays is going to be travelling with the ether wind, and the other one's going to be trying to cut across the ether wind. And of course, the one that goes across the ether wind will always arrive ahead of the other light rays. Well, how do you know if two light rays are arriving ahead or behind each other? Because the time differences would be microscopic, immeasurably small. Well, this is where the interferometer comes in, and it was very, very clever. If two light rays arrive at exactly the same time, you can see that they're going to constructively add together. But it only takes a tiny time difference in the arrival of those two waves. I mean, the time between the crest of one wave and the crest of the same wave is very, very tiny. So to be out by half a wavelength is the tiniest increment in time, and anywhere in between. And of course, if they're out by half a wavelength, they're going to destructively interfere. Well, we see interference patterns around us all the time. You think about just a mesh door. If I bring another mesh door in front of it, you can see that the tiniest movement of one mesh compared to the other gives you very large changes in the interference pattern that you see between those two as they come back in, which is exactly what Michelson and Morley were looking for. They weren't looking for an interference pattern. You're going to have an interference pattern. What they were looking for were the tiny changes in that interference pattern as they rotated their apparatus through 90 degrees, and as the two light rays should have changed position as to which one was arriving first. There's going to be a slight change in the arrival time between one light ray and the next, which should have led to a very visible and massive change in the interference pattern. And here's the outcome. They didn't discover any difference as they rotated the thing. The interference pattern did not change. The light rays both continued to arrive at the apparatus in the same relative phase, however much you rotated it. In other words, they got a null result. They were trying to measure the speed of the Earth through the ether, and they failed to find any speed of the Earth through the ether. So they thought, well, maybe we just happen to be travelling with the ether at the moment. So they waited 6 months. Of course, then we're going to be on the other side of the sun, travelling the opposite direction. If we were travelling with the ether wind then 6 months later we must be travelling against it. So they tried at different seasons of the year. They tried at different altitudes. Every time they tried it, they got a null result. Probably the most important null result in physics.